Hello everyone. Today we are going to understand the root locus techniques, how to plot a root locus, silent feature of root locus, and the general procedure of root locus. So to understand what exactly the root locus is, so we will begin with this simple example. Consider a unity feedback system with open loop transfer function as a k upon s plus 1. Here you can understand that there is one open loop pole, there is no zero, and the system is described by a static gain k. So when you equate this denominator with equals to 0, so you will get the open loop pole location, and it is at s is equals to minus 1. This procedure requires characteristic equation, and therefore the closed loop transfer function of this system, that is C by R ratio, is equals to k upon. After solving, you will understand this becomes k upon s plus 1 upon k, whereas this denominator of closed loop transfer function is the characteristic equation. So now equate this characteristic equation, or let us rearrange that characteristic equation, equate that is equals to 0, and therefore for rearranging for the s, it becomes s is equals to minus 1 minus k. Now as I told, we are going to vary system parameter, so let us start varying this k from 0 to maximum. When we substitute k is equals to 0, we will have the pole location at s is equals to minus 1. Now when you substitute k is equals to 0.50, 1, 2, likewise the pole location according to this equation, it is going to vary, and it is shown here. So the pole location gets shifted to for k is equals to 0.5, it is at s is equals to minus 1.5, likewise minus 2, minus 3, and for k is equals to 15, it is at k is equals to minus 16. When you imagine k is maximum value, then again the pole location it will vary, and it goes towards the negative real axis on that side, left hand side. So the definition of root locus is, it is a path of roots of the characteristic equation plotted for in the s domain or in the s plane as the system parameter k varies from 0 to infinity. This is the standard definition of root locus, which you have to remember. So one way is compute, if you have the characteristic equation, rearrange it for s and get the multiple values or the sufficient values to have the locus of roots from minimum k to maximum k, or from 0 to infinity. But if we have a higher order system, for example, in this system the number of open loop poles are 4. So taking closed loop transfer function and that to be the characteristic equation, this denominator will be the characteristic equation. Again when you equate it, it equals to 0. So, and after substitution of multiple values of k beginning with minimum to maximum, it becomes very difficult to compute the various pole location. In this case we have to compute for 4 locations, so it becomes difficult. So the scientist W.R. Evans, he has developed a simple method for finding the roots of characteristic equation, and generally he proposed the theory, and which is come out as a root locus technique. So we are going to understand the procedure which is proposed by the scientist Evans. So So to understand this root locus technique, I would like to explain with the help of these notes. So let us begin with, when we have either open loop transfer function along with feedback transfer function. So if the arrangement is like this, then always the procedure begins with this characteristic equation: 1 plus g of s into h of s is equals to 0. So for root locus and from characteristic equation we require two things. One is the magnitude, mod of g of s h of s is equals to 1, and the angle that we will understand with the help of some examples. So let us begin with another example. Let's have another example in which this parameter g of s h of s is given as k into s upon s plus 1. Here you will clearly understand that the open loop zeros are 1, which is located at origin, and the open loop pole, when you equate this denominator to 0, so the position or the location of open loop pole, it is at s is equals to minus 1. So let us start the procedure. Get the characteristic equation of closed loop system. As readily we have g of s h of s given in the statement. So after substitution of that and after simplifying, we will have the characteristic equation in this form: s into k plus 1 is equals to 0. When you rearrange this equation for s, so you will have this simplified expression. Now, as discussed earlier, let us have the multiple values. Let us compute the various locations of this open loop pole. When you vary k from 0 to infinity, for example, here by substituting this k, then we will have the locations for corresponding values at minus 1, minus 0.5, minus 0.1. It means that the original root, when system parameter is 0, at that time it is at s is equals to minus 1, and this root starts moving towards origin or towards the open loop 0. So this is considered as a root locus plot, and this is the path of that root which starts or which originates at s is equals to minus 1 and it terminates at s is equals to 0, where there is the open loop 0 position. So in the form of the system parameter k, the root, it starts from k is equals to 0 and it ends with k is equals to infinity. Let us summarize this root locus plot. The number of open loop poles p is equals to 1, which is at s is equals to minus 1. The open loop zeros, can you find out it? Yes, it is at s is equals to 0, and the number of branches of this locus are only 1. Let us have another example. Here we have two open loop poles, one at s is equals to 0, another one at s is equals to minus 4. There is no open loop 0 and the system parameter k is specified. Again we have a unity feedback system. So the procedure again we will start with this characteristic equation 1 plus g of s h of s is equals to 0. After substituting this open loop transfer function and the unity feedback transfer function h of s, we will have the simplified characteristic equation, which is s square plus 4s plus k. Here the characteristic equation is the quadratic equation, and we know if we have the quadratic equation a square plus bs plus c, then the roots of that standard equation are given by the standard solution, which is minus b plus or minus root of b square minus 4ac upon 2a, where a is the coefficient of s square term, b is the coefficient of s term, and c is the coefficient of s raised to 0, or it is a constant one. So after substituting this, we have two roots s1 and s2, and the formula will give you the simplified form as a minus 2 plus or minus root of 4 minus k. It means that we can choose s1 is equals to minus 2 plus root of 4 minus k, and another root as a s2 is equals to minus 2 minus root of 4 minus k. Now, as discussed earlier, let us vary k. So when we start the compute calculations with k is equals to 0, in this equation, then we will have s1 root as a 0 and s2 root as a minus 4. Clearly, when you substitute k, then this root term becomes only 4, and the root of 4 is 2. Therefore, you can understand how it becomes 0 and minus 4. Likewise, when k is equals to 2, we will have another solutions for s1 and s2 as a minus 1, minus 3. And likewise, go on varying k, 4, 6, maximum. Infinity means take a max value. Now here, as we have two roots, see the roots are starts moving towards negative value. This root, it's moves from origin to minus 1, minus 2, and look at this value. The real part remains same, but the imaginary part is going to vary on positive j omega axis. Likewise, this root, earlier it was at minus 4, then it comes to at minus 3, then minus 2, and for the other values, the real part is again same, and this root, it moves towards it moves parallel to negative j omega axis. So when you plot this, we will have, see, the locus of the first root, it moves from origin at minus 1, minus 2 for sample values, and it moves like this. Similarly, the other root, which is s2, this approaches towards this minus 2. Up at minus 2, the locus breaks and it approaches, the s2 root approaches, it moves in this way. Okay, so this is the root locus. Let us summarize again this root locus. The plot of s1, it moves in this way. The plot of s2, it moves in this way. So number of poles are 2, number of zeros are 0, and the number of branches of root locus are 2. So using time domain analysis, when the value of k is between 0 to 4, then we have real roots. The roots are lying on a real omega axis, of course in the left half, so system is stable, but